Hello everybody and welcome to our today's webinar from Vector on the efficient development of driver assistance systems and HAD with vADASdeveloper. My name is Alex. I'm a business developer for vADASdeveloper and for our driver assistance tools in Vector Measurement and Calibration Department, and with me is my colleague Mohammed.
Hello everyone. I'm Mohammed Ballouk. I work as a field application engineer and do customer projects.
Okay, thanks, Mohammed. So in today's webinar, we're going to give you an overview on vADASdeveloper and how to do algorithms with the tool. So very basic, let's say, mappings of sensors to objects in the Visual Studio environment using vADASdeveloper. Just a few organizational things at the beginning. So if you have questions, we would prefer to answer them at the end of the webinar. So please post them in the Q&A window to all panelists so we can see them later on at the end. And if there should be problems of any kind, if you lose the audio or something, you can put that in the chat window. We have a colleague here who also takes care of the technical part for the for the media stuff. Okay. So having said that, let's start with the webinar itself. So we will have the webinar split in two parts. I will do the first about 20 so minutes to give you a rough introduction about vADASdeveloper, what are the use cases, what are not the use cases, who are the target users, etc. And the second part of the presentation, my colleague Mohammed will give you a tool overview and show you some of the features that are there in vADASdeveloper to tap sensors, to get sensor data into your code and also to visualize stuff on screen. Okay, so let's start. How does a typical sensor setup for ADAS or HAD look like today? So what we see very often are setups that contain a front radar coming from ACCs, being extended with a front cam. So those two sensors are very often used for AEB systems. In the next level of autonomy, you could have corner radars and a fusion ECU, because you need more processing power now to calculate all the sensor data fusion, for example, or the environment model. And in a later stage, you could also extend that again with a rear cam, a rear cam, and the side LIDARs, so you get a better overview even of the 360 degrees of the car. And these are just the automotive sensors that basically you want to use for your project, but also you need then context cameras and other reference systems like other LIDAR systems to get ground truth data for your tests and for your algorithm development, especially for the validation of the algorithms. So all those sensors, they live on different network systems. So typically the radars today, most of them still in those projects we see here, they are connected on CAN. There are a few on Ethernet coming up. There's probably also FlexRays around, but typically still I would say it's CAN or CAN-FD as of now. Then we have the LIDAR. So here you could use automotive Ethernet or you could use just the normal Ethernet. This depends on the project. And you could have for all the reference systems, typically because these are non-automotive sensors, you have either a USB connection or some normal /gigabit Ethernet connection. So to all of these sensors, you need to get access in your data fusion or in your algorithm prototyping project. What are now the use cases for prototyping and what are the linked tool requirements for that? So first one is, of course, the data recording. So you want to get access to the sensors on the different networks, and you have typically a very high recording bandwidth for the sensor data. So this is basically the source of everything. You need to get access to whatever your system provides you. And second would be you want to visualize that data. So you want to visualize detected objects from each sensor. Maybe the fused data, or very sure if you do a fusion project that you also want to visualize the fused data and the environment model. And you also want to visualize images from reference cameras and LIDARs, and of course also things like vehicle state data like speed, position, and course. Just fix this. Okay. Then you go directly into the code development. This is basically your most important use case. This is what you want to do. You want to develop your algorithm, hopefully with as little as needed interference with some outside infrastructure. So you want to dive into the code development. So you typically want to use an OO language, so an object-oriented language, especially for data fusion, or just because it's modern. And in prototyping, you just want to be fast, and you're much faster with an object-oriented language. Second thing is then you want to use the recorded data from the recording stage to replay that sensor data typically to your algorithm under development to stimulate your algorithm. And for that, it's very important that you have also a feature of synchronous debugging, so you can stimulate your algorithm with some data, and as soon as you hit a breakpoint in your algorithm, that the data stream at that point would also stop, so you can step through your algorithm without keeping the link to the external, let's say, stimuli, and also be able to have, let's say, a meaningful way through your algorithm. And at one point you say, okay, now I'm done with that subroutine, for example, or that method, and I'm good with it. I just want to remove that breakpoint and keep on stimulating, and then the stimulation with the recorded data will commence from the same point where you stopped, and not being flooded with some data when you run into a breakpoint. And the last one is finally the algorithm validation. So you want to run your algorithm typically in a parallel execution mode, if you wish, without a GUI against some test and reference data. This is why we use this server symbol up here. So very often it's without the GUI, and it's controlled by a master logic where you basically sift through a lot of data. You put a lot of data onto your algorithm and see how it reacts, and also calculate the metrics and again put that somewhere. So you also want to have a remote control by a master application, some kind of test logic, and this leads then finally to some, let's say, requirements referring to interfacing of your application to something else outside. Okay, so what are the contents of Vector's ADAS solution with respect to algorithm prototyping? So we have a tool, vADASdeveloper, vADASdeveloper, and it's the development tool for implementing, debugging, and testing multi-sensor applications in Visual Studio. And it says in C# and C and C++. So let's say the core language in vADASdeveloper is typically .NET, C#, but of course you can also use C and C++ libraries and use them inside your code as a computation engine. And here you can use pretty much every C++ library that is available. Especially if you're looking into data fusion, there is a product from our partner company Base Labs. It's called Create. So that is an algorithm toolbox, a library for sensor data fusion, probabilistic filtering, and tracking. And both of those products, they are, the typical user group is algorithm and function and fusion developers. And especially in the last one, we will have a webinar on Create in a week from now, December 11th. You can also register on Vector's website for that. Okay, so today we're going to focus now on vADASdeveloper. So this is the infrastructure tool which is used to bring in the sensor data, log them, visualize them, and stimulate your algorithm with it. So how does it look like? This is how it looks like. So we have vADASdeveloper being integrated into Visual Studio. We provide you with a whole block set for different sensors. So for example, webcams, and also we'll see that later, some LIDARs. We have a so-called Canopy source block. This is basically the access block to all the networks. So it's not a separate license, but it's just using the Canopy core technology. And this is why we called it the Canopy source block. And it also supports all the networks that are supported in Canopy. So the idea is you have some source blocks on the left, then you have some kind of a processing block. This we do not provide. This is what you have to do. This is basically the product of your work, that you make a component that has your algorithm. And on the right hand side you see the visualization blocks, which will then be used to show the results from either the incoming sensors or some kind of processing stage somewhere along the line. As I already mentioned, it's integrating Visual Studio, so the output is an .exe file, and we provide all kinds of different things. So I mentioned that we have C#, C++, and C, or anything that you can interface to a .NET language. And again, it's a tool for code developers or for fusion developers. It's not so much a tool which you typically use so much in a car. You, of course, record the sensor data in the car, but typically the use case is rather getting the data in and then working on the desk, or later on a server if you do validation, working on the desk of the developer to get the algorithm running. let's say, focused typically on prototyping of that. We do not provide production code for ECUs. So it is for prototyping for people who do prototypical algorithms, maybe as part of the requirements phase, or maybe as just exploration to find out what is the right thing to do later on in the embedded controller. The framework is extensible with user-built components, so that's the main focus, that you do data fusion and other things, like, for example, image processing for classifying images, or let's say objects inside images. If you want to experiment with some kind of algorithms from image processing, or also there are libraries for point cloud processing out there, and all of those, if they have a standard, let's say C++ API or C API, you can interface them inside vADASdeveloper. And the GUI, so that the visualization, could also be expanded, because if our visualizations, which you'll see in a minute, would not be enough for your project, you can also build your custom GUIs, because finally it's Windows programming. And the nice thing is, so if you need something special, especially for the visualization, and also on the other side, for the driver side, it's Windows program, it's Windows C# programming, and the person doing that doesn't even have to come from the automotive background, so it's probably also a little easier to get things being done outside of an automotive company, get a freelancer, something like that. Okay, built in is the high-performance recording engine from Canopy. So here we use the same base technology as Canopy. We won't go into details for that, but with Canopy we record all kinds of, let's say, ADAS systems, which have a diverse setup of different sensors, and the commonality is that it's all at the very high data rate, where we talk about up to 1 GB a second for one recording machine. So we have a very high performing recording engine below. We replay the data for offline analysis and debugging. We'll see that later. We have different data formats, the most important ones being MDF and BSD for us, but also custom file types, or for example reusing or using ADTF recorded data would also be possible with a custom component that you could write or we could do as a part of a project. This one I already mentioned, Visual Studio, and the output is a Windows XE one application, which will then contain the, let's say, the recorder, the data recording, the data replay, and also your algorithm. Okay, now let's look at the different use cases. Step one would be the sensor data recording, the visualization on the right-hand side. So here I'm using it's not a screenshot actually from our tool, but it's the same, let's say, visualization. We use the components as they are modeled in vADASdeveloper. On the right you see the visualization. There is in the middle, you can see there are no algorithms yet. There are just the sources. On the left we have used a webcam, supplier radar, a component that's mobile, it's called Mobileye Cam or whatever. So the most important thing is there's no algorithm at the moment. You just record stuff from your car or from your setup. And what is available for this? So we support arbitrary sensors on CAN, FlexRay, Ethernet. We support PDUs, static PDUs, to some parts also some IP on UDP. We support XCP as a calibration protocol, so you can also get data from inside your controller if you want to use that in the application. That's also very interesting sometimes. And you can also integrate your own sensors. The recording is done into BST format, that's our serialization format, and MDF. MDF is a standard for measurement data recording, and we use this very widely inside our department and also inside the vector tools overall. Okay, now let's look at the Canopy source component. As I mentioned before, this is needed for accessing all the network components. So everything that, let's say, make it simple, lives on CAN, for example, you can use, access via the Canopy source component. What can you do there? So here we provide an embedded editor in Visual Studio. So that's part of the delivery of vADASdeveloper, that you can now deliver, you can configure, the sources from which you want to see and record data. So CAN, LIN, FlexRay, or also analog digital values, also possible. Automotive Ethernet, ECU debug information, anything more or less that Canopy also can access, you can use in vADASdeveloper. Once you have done the device configuration, so once you have told which, for example, network you want to measure and which DBC on CAN you want to use, you can then select the signals that you want to see, because not all signals typically are relevant for your application. And then, so here this is just the graphics of the selection of the signals. Here you can see to the left, you can see the device configuration where you have CAN, CCP, XCP devices, different Ethernet things, and so on. And then you can also select the signals here. And the important part comes now. After having selected the single signals, which typically come as scalars, we have a mapping to data objects. Because I mentioned before that typically in the algorithm development, especially in prototyping, when you want to be fast, so speed is more important. Speed of development is more important than necessarily the last, let's say, real-time requirement, or just getting things fast makes a lot of sense, especially in fusion, also in fusion controllers of the future. We see a lot of things happening now, especially in C++, not C#, of course, but a lot of C#, C++ things happening. So object orientation is becoming more important in the world of automated driving than it had been in the world of, let's say, classical control engineering like controllers till date. Okay, what do you do in the so-called signal-to-object adapter? The idea basically is that you have an application class, for example, a radar object, or in this case, a GPS object. The GPS object is really one container that contains all the information of the position, of the speed, of the course, of anything that comes with GPS, and it's contained in one object. And this is an application class, but on your bus, on your network system, you have a serialized information. So somebody sends you a GPS X signal or a GPS Y or a GPS course or whatever. But you don't want to treat signal by signal algorithm, but rather you want to, let's say, assemble all the different properties that you get by the signal into one single container, and that would be the GPS object. So first you select the application class to be used as a target for the mapping, and then you would drag and drop the signals into the different properties of your class instance, or in your, let's say, prototype instance. And then as soon as all the information is collected, let's say the N signals have come in from the bus, from the CAN bus, which describe your object in its entirety, then only then an object would be created and then delivered via a pin to a processing component. That's the use case of the signal object adapter, and we also see that in a minute. Here's just an example for a newer feature. So here we see just we have a signal object converter for object lists, because today many of the, for example, radars or the smart cameras, they send object lists of what they detect, and there are different mechanics for that on the network. So for example, one mechanic is that you get an announcement of how many objects will come out in the next transmission of the sensor. Then it will always use the same ID, CAN ID, for the different objects. So it's always CAN ID 101 in this case, but the object ID is 1, and then you get the properties of the first object. And then you get another transmission on the same message, and you get object ID number 2. So this is a different object, but again on the same message. And in this case, you would get constructed an output of an object list of 2 items on IDs, on identical IDs, CAN IDs and signals, and the same thing now with 3, and then you get 3 times, and then you get a list with 3. And this method of, let's say, well, how to communicate, how to serialize information on CAN bus and how sensors do that, we call this modulation-based, and hence we made a modulation-based converter. And for example, the ARS 408 radar, some of you might know that. Such radars, they use this kind of scheme. There's also a different scheme that is used in Mobileye, the dev kit, that works somehow different. For that, we also provide a converter, but in the core, you fill it with your code. And in the core, basically, it's the, let's say, the creation from the signal layer, or from the signal abstraction to the object abstraction inside the code. So now let's look at in the visualization down here. What is available for the visualization? We have an overlay of the videos with the objects. So for that, we can also calibrate the camera or video images. We have the overlay of a GPS information in an OpenStreetMap-based GPS window to see the position, the course of the ego vehicle. And you could also, let's say, if you wish, you could also superimpose in this picture, you could also superimpose the some detections. For example, if you have some map information about a traffic light, it says position, latitude, altitude, etc., longitude, then you can also place it in the window here. And finally, we have a so-called scene window. It's a 3D. It's a hardware-accelerated 3D display of the environment of the eco vehicle, into which you can also plot different things. And here we provide different graphics objects that can be then connected to application objects to, let's say, be created and also to be displayed at their, let's say, positions. Because so in here you see a typical thing. So this is just gives you the two fields of view of different sensors. Then you have those boxes. They might come from a radar. Then you have those circles. They might come from a smart camera. And this is just possible with a few clicks inside vADASdeveloper without too much coding to get such a visual representation. Okay, now how does this look like? Again, same thing as before. On the left, now you do not see signals, but you see now objects, because here we visualize all the output pins from objects, from components. You drag them in here. You would say, okay, I want to, for example, visualize my radar detection as an ellipsoid, and then I map my graphical properties or the properties of the graphical component. I map to the applications object properties, and hence the application object controls the appearance where the graphics object will appear, and it would also control its cardinality. So if you map one item and there is a list containing 0 objects, you will see 0 objects, and if there is a list with 100 items, you will get automatically 100 objects being displayed, for example, in the scene window. There is also a camera calibration tool, I mentioned that before, which allows you to do the intrinsic coordination of the cameras, and then it's somewhat easier to get the overlays properly in the video window. With LIDARs, we can also work. So in the 3D scene view, we have the LIDAR point cloud as a graphics object that you can easily display, and we support the usual suspects, if you want, of the LIDAR, so the Velodynes, the IBOs, and also Quanergy M8. Till now. Step 2 would now be develop your algorithm in the lab. So now instead of the live data, you would use a player. You can see this on the left. In the player, you would replay the recorded data, and now you would build your algorithm. Here you see the input pins of the algorithm, and then you would develop whatever is the content of this. Either it could be a data fusion, you do it from scratch, you have some modules in C++ or C you want to use, or you could, for fusion, also use Baselab's Create. For if you want to do image processing, you can go into OpenCV, you can do anything GPU accelerated, as long as it's some kind of C++ interface, and you can use this in a Visual Studio project, you can also use it in here. As an example of what could be an algorithm inside, we will see some of them, very simple ones and more complex ones in Mohammad's presentation in a few minutes. I've just put in the target for Simulink coder, because for Simulink we also provide a so-called vADASdeveloper target. So this means you can compile your Simulink model into a C++ DLL. This will be wrapped, or sorry, it's maybe a CDLL. It's a DLL that you can use, and we provide a C# wrapper for this, so you can call this DLL then from within your code, and then you can, for example, include such a controller model inside your vADASdeveloper application. This requires only a few adaptations of component pins, but in general the idea is reuse the knowledge that you've put into the Simulink model and drive it with the data directly in vADASdeveloper. Okay, and step 3 finally would be the algorithm validation, and here we have, I mentioned in the beginning that you could do this on a server, so there's different ways how to do things and different use cases. One use case could be that you have a lot of scenario data, let's say 10, 100,000 scenarios, and you want to test the same algorithm against that scenario, and the scenario would also include pre-recorded golden standard / ground truth data. That you could use in vADASdeveloper because there's a run license available. But there's also another use case possible that you would want to stimulate your model, maybe because you have a closed loop reaction of your algorithm, and you want to do that against the virtual scenario framework like pre-scan from TAS or IPG Car Maker or VRES, or there's a couple more of those environments around. And you could do a coupling to vADASdeveloper, for example, via FMI, FMU if it's control information. It's not so well suited for object information, but there are different methods for that. And the whole thing could then be controlled by Canoe as a test controller. And so you would have here kind of a test system, and the test cases could be done in Canoe or in vTest Studio. You could then have a closed loop testing system which runs through different scenarios and then use different parameters to check your algorithm behavior. Okay, having said that, I just want to quickly go and show you what system we use for the demo now. So we have a simplified setup here with a front radar. This one is on CAN and goes into the PC with a BN1630A, so one of our CAN interfaces. Then we have a front camera which comes on USB, just very simple. It was really a web camera in this use case. And then a surround LIDAR, it's Velodyne VLP16, I think. And all of this is then going into vADASdeveloper. Here we simulate it, so we pre-recorded that, and Mohammed will replay this from our other PC. But in reality, you would also then see that from the sensors. So now you have an idea what is in the demo setup, and now I will hand over to Mohammed for the tool demo. So once again, if you have Q&A questions, just put them in the Q&A, and then later on we will answer them after the tool demonstration. Thank you. Mohammed, your turn.
So, hello everyone. Thank you for joining our webinar today. Just before I start, I'm going to start Visual Studio and start by developing a new application. But before, let me show you exactly what we are going to see today. So basically, this is our complete project. What we will see is we are going to cover all the use cases Alex talked about. So basically, we are going to access the data, process the data, record, and view the data. For this, we have here our Velodyne component. It's the data source. We are getting data from Velodyne. We have Canopy that will provide us with the data from the cam, vehicle cam, and data from the radar as object overlays, and the data from vehicle. Later on, we are going to use the recorder to record these data into a file, into a binary stream file, which is supported by vADAS, and visualize the data. And in the next task, we are going to use a player to play all these data that we recorded with this recorder. So to start, I'm going to start now my my application. So 1 second. Here we go. I'm going to start now my simulation, and and here I'm going to switch to live data, click on start, and as you can see, this is how the data will look like. Basically, I have a video cam. I have here my video cam together with this yaw rate, which is coming from the vehicle on CAN. I have also here some detections from my radar, and here you can see basically these gray points are the point cloud that are being recorded by the Velodyne. I can switch the view inside this scene view. Okay, basically this is what we are going to develop. What you are seeing also, we have right here something called task. We'll be covering this also, and one more feature which is by changing. So when we are going to process the data, so we've written a small component which will then change the image that we are seeing at the moment. Let me run the so let me run it again and then open the setting window again. And you see we have here my processing. I'm going to switch just the color of or flip the image using C++ code, or I'm going to make it gray. And these data are done in code. So we are just processing the image data in code. Okay, so I'm going to stop now the application, close it. And we will start doing this from scratch. I won't be showing everything because it will take a lot of time, but I will try to show you everything you need to know. Basically, I'm going to switch now to my second project. This is a project, just it should look like exactly the same like the one I showed you. I started by creating an empty project in Visual Studio. We have some templates that you can use. I just selected the empty project and then started adding the component that I need. What you are seeing here is the Canopy component and the visualization component. You can add them by right-click on the project name, select Add, and go to Component. And here you can see the list of all the vADAS components that you can use. I selected Canopy, and I also added a visualization component. Later on, we will also use this player to replay our data. Let me cancel this. Okay. What you also see here is basically when you created this project, Visual Studio will give you back a WinForms project. It will just add an ADL file, which is application description language file. In this file, if you open it, there's a visual editor, which will help you set up your project. So basically, before you start coding, you can start by accessing the data using these components, and later on, if you need to code something, then you will get also help from vADAS on how to write the code and start using it. Okay, so this is the ADL file. Basically, this is where you do your setting, do your component. This is the Canopy component that I added. I'm going to open it. As you see, it's also an editor. I've already made some setting inside, so basically I will just wait till it connects. Just 1 second, please. Okay. So now here, if I open this device configuration, this window will open. So basically I have here a list of devices. I already added the devices, but basically it's very easy. You go here to devices, click on new, and now you have access to all the Canopy devices that you can use in your application. For my demonstration, I use a CAN monitor to get the data from the vehicle and to get the data also from the radar. I also used a camera file to get the data, to get the video images from the saved file that I did before. Okay, now adding these monitor and this file, when you click OK, it will ask you, in case of CAN, it will ask you for a DBC file. Just select it, set a new network, and you are set. Now we have here the networks. One more thing we need to do is to select now the data that we need to record in our vADAS. Just like Alex said, so I'm going to close this device configuration. We already configured our devices. I go back to my measurement configuration. Just 1 second. So here's the window. And now you see here are my devices. They are online. If I now go to measurement signals, right click somewhere and say insert signals, another small window will open. And now you can select which signals you are interested in. Let's say from the cam, you can select, I'm sorry, here is the window. You can select the camera. So this is the video. Basically, this is the video stream. Or maybe if you want to add some signals from the radar, it will be somewhere here. So you can choose the radar DBC file, switch to signals, and add the signal that you want. So this is a view of the signals. You can select the signal you want and click apply. It will be added, and then you can use it in your vADAS application. You can sort them using the source, then you know exactly the message name, and here is the signal name. I've done all this. So basically, these are the signals I'm interested in. This one comes from my vehicle, and it describes a yaw rate of the vehicle itself. And here are some objects that I will use later to show the objects from the radar. Here is also my vehicle cam that will show the video itself. For the signals that you are using in vADAS, it's important that you select, you check these checkbox in the vADAS recorder column. So these signals will be available. Okay, good. Now here is also the recorder. You can choose where to save the data. this applies to the MF4 data with MF4 file, which will be recorded by Canopy. Let me close this. Okay, basically we've done our device configuration. We selected the data or the signals that we need. And if you see here, Canopy already says we have some sources. So the source is Canopy, and it provides us now with the signals that we need to that we can use. But basically, you can see also it needs a signal-to-object converter. Okay, for this we are going now to write a small code. Basically, two classes. One will contain the yaw rate. So it will be an object which includes the yaw rate itself, and the other object, the other class will be an object description of the radar recognitions. So let's start. I'm going to close this. I don't need it. I'm going to click on no. I'm not saving anything. I've already started. So basically, this is very easy. I've written a small class called yaw rate. It's public. It should be public because you are accessing it. It has one property of type double and a small constructor to build up these class, to build up this project. Okay, since we are going to use this in our vADAS, I need now to write a signal to object converter. Also very easy. You start by typing a public class, so it should be a class, a public class, and you start giving it a name. So yaw rate, I'm going to say to call it as converter. Now you need to implement basically the interface that Alex already talked about. It's called the iSignal object converter. And you see now it's showing an error. It needs a type. So it's saying, okay, what should this converter convert the data into? So basically, I want the return value of this converter. It should be of type yaw rate. Okay, it's still showing some error because it's saying, okay, you didn't implement the interface. It's in C#. You need to implement the function of that interface. Visual Studio offers, or ReSharp in my case, but Visual Studio had this feature also. It offers you to implement these two functions for you. Basically, it's just implementing the missing function of the converter. Okay, we have two functions inside, one called convert. So basically, this will convert the signal into object. And the other one is called canConvert. So basically here you can evaluate if you want to convert these value or to convert this signal, or you just want to ignore it. In my case, I need to convert, or I want to convert everything. So I'm just typing return true. But you can also say, return. Let's say I'm just interested in the if the yaw rate is larger than 0, if it's positive. For this, we still need to define one thing. So basically, now we need also to define the property where Canopy should put the signal into. So basically, it's a public, a double, and it's public double yaw rate. I would write Canopy just next to it, so you will see where it comes from. And now get and set. This is all what you need to do. This is just telling because the can I've written it in capital letter, so it's no issue. And now I can say here, canConvert. I can say return my yaw rate Canopy larger than 0. And in this case, oh, I'm sorry. So it should be larger than 0. In this case, it will only convert whenever Canopy delivers this value. It will be only converted into an object and will be later on visible in our visualization component if I have the yaw rate larger than 0. But in my case, I really don't need this because I'm interested in all the values, so I'm going to leave it as return true. In the convert method itself, all I have to do is return the new yaw rate. So basically, it's of type it's of type yaw rate. This is what the converter is returning back, and the double yaw value is basically this property value. So yaw rate Canopy, and just because it's a small value, basically I'm getting a very small value out of this yaw rate. I'm going to multiply it by 8. So basically I'm processing the data somehow, and I multiply it by 8. Okay, good. Now I'm going to save this, close it. Let's build our project again. So Canopy will be aware, all the other components will be aware of our changes of our converter. if I open Canopy component again, then it needs to be connected, but you can see now under the signal object converter in the list, I have a yaw rate converter. So basically, I can convert now data into this yaw rate. Drag and drop it right here. It's saying, okay, I still need this property. So basically, you are binding the signal coming from the Canopy component, the Canopy CAN component, into the property in my converter. I'm going to search for it in this list. Basically, it should be somewhere here. So let me check. So this is the value that I need. When I connect these, let's say I connect these property to the CAN signal, this becomes green because now it has all the properties, everything is set, and now it can be converted. Let me close this down. Okay, now we've seen the iSignal to object converter, but there are also some other converters that we need. In our case, our radar will deliver basically a 5 objects at the same time as a measurement, or let's say 6 objects or whatever. So the radar will tell us over CAN, it will send a message saying the next measurement is done for 6, or I recognize 6 objects. So basically, I have a number of objects, and then it will start sending me back the data of these 6 objects over CAN. Okay, for this, I also set up now basically also the same class. You see, it's whenever you are writing a converter, it's easy because all you need to do is just describing these objects. In my case, my object has an ID. It has latitude, longitude, a width, and a length. And I just made also for easy doing, I just added a constructor. Basically, what we are going to do is now repeating the whole thing that we've done. Now we are writing a converter, which will convert the data from Canopy signals into an object of type object overlay. So basically, here is my converter. Okay, since now we need to build a list, and not only one object, so we need to build a list of objects of all the recognitions of my radar, I'm going to use here the dynamic, so the modulation converter. So let me write it here, and it's basically dynamic object modulation based converter. And again, it's asking me, okay, what type of data I'm going to return back. So basically, I'm going to select object overlay. Basically, it will return back these objects, a list of these objects. Okay, great. So now, basically, I can also copy these properties because I'm going to use them. They need to be binded to Canopy. And I also need to implement the interface functions. So here we go. It's already implemented. You can see it also has these convert and can convert. I'm going to just write here next to it Canopy. And just to make sure that you see the difference here, everything is binded now to Canopy signal, Canopy, and the last one is the length. So the name is Canopy at the end. Now I will convert everything. Also, I'm not going to do anything with the data. I just need to everything or all the data be converted. And here by the convert, all I need to do is I need to do return, new, and object overlay. And now I need to fill up these data. So I have the ID, and then I have here the latitude, I think exactly, and then longitude. And I need the width, and I need the height. It's called length. I'm sorry, it's the length. Exactly. So now we are done. Basically, we have the object, and we have now a converter that will build up these objects out of the Canopy signals. Let me save this, close it. If I build my project again, go to Canopy. Again, we will have also these object overlay. I'm going to drag it here. one thing that we didn't see is this count. This is an extra property because now we are saying we need to build up a list of objects. So basically, we are going to fill these data, and this count is also coming from the radar itself. The radar sent me the number of objects. This is the signal. So now I just need to bind all these data per drag and drop. It's very easy. And object ID. Now the length, and we still need to bind the width. Okay, great. So now the data are bounded. Now we have our data source. Let me close this. You know, after each change in any of these components, you need to rebuild your project because all the other components should be aware of the changes you've done. Okay, now I'm going to switch to my visualization component. So here, it's very easy now. We set up now the data access, so we have access to our data. Now we need to tell vADAS how to show these data. Basically, these are now our objects. So now we have the Canopy image. I will ignore this for the moment. Now we have the object overlays. I'm going to drag and drop right here, and the yaw rate. Okay. Now it's asking how should it looks like? How should the GFX object looks like? So basically, I want to make a cuboid out of it. So the object overlays and the yaw rate should be displayed as a triangle. Okay. You have here the different coordinate systems. In my case, I want the yaw rate, so it should be a triangle just rotating on one axis, just like a compass. I'm going to say it depends on the view coordinate because I just want to use it as a pixel, so I want to set it somewhere on the screen. I would say it should be displayed on the x40, so pixel 40, y is 40. The rotation angle now, if you see now, if I click on this icon, the value is not static anymore, but I can convert it into a dynamic value. And this dynamic value, is, if you remember, it comes from the converter itself. This is what we are basically calculating. So I bind now the rotation angle. It should now change whenever the value from the CAN bus changed. Okay, the fill color, this is the object, how it should looks like. So I choose this blue one. And now the size of these, of my triangle, I'm going to set it to 30 and 20, maybe a little bit bigger, so just make sure that it will be shown. Okay, now it's set. The object overlay, we still need to do the same thing. In this case, we are leaving it a Cartesian coordinate system. We need to set up the data, bind up the data. So basically, this is the X position. All I need to do is click on this icon, select now the data. So X is basically the lat. Y is now the long. Z, I will leave it by 0. Then now the depth, it's basically the len. If you see, you can change the name. So basically, when you write these converter, you can change and choose the name that you want. The height, I will leave it by, let's say, let's leave it by 2 because I don't have value for the height of the object from the radar, but I have the width. Okay, let me choose now the fill color of my object. So I'm going to choose the yellow, and this is the stroke, and basically this is all what we need to do. Basically, it's now set up. Let me save it. Okay, now we set up the GFX configuration. We still need to do one more thing here in this visualization, and basically we need to add the views. So we need to tell where to view these data. I've already added one. So if you see here, you have this plus sign, it's adding view. We have different views. One of them is the video view. I'm using it to show my vehicle cam. And here you can set up which of these GFX configurations should appear in this view. Basically, I don't want this cuboid to be viewed in the video, and I don't want the triangle to be viewed. Okay, now we can set up our scene view. We also have the map view, but it's just if you have GPS data. I don't have them in my demonstration. But I will set now a scene view, basically this 3D view. Okay, and this should displaying both data. For me, I want these both GFX objects to be displayed in here. Great, good. So that's everything that we need to know at the moment. You can give it a name. I'm going to add one more view for my Velodyne. and I'm going to call it right now Velodyne. And basically, I just want everything also to be displayed right here. We will also come back and define the point cloud that will be displayed in this view. Let me save it, close it. Now I need to rebuild, as you know already. If I now go to my application ADL, where I do the settings and all these components, where I add the components to my project, you now see that we have data coming from Canopy, and we have pins, the input pins for our visualization component. If you click right here, vADAS will tell you exactly which pins get together. So basically, you can't do anything wrong. So I'm going to connect them exactly like vADAS tell me. It just says that these pin, this is the output pin, has the same data type like the input pin in the pin of the visualization component. Just let me connect everything. So they are connected now. Okay, we are missing one more, two more steps. So basically now we need to define our main form. In main form, we need to add the visualization component. So we see in our user interface how the data will look like. For this, I'm going to switch back, or let me first define the Velodyne here. So basically, we have to open the main form once. Okay, so you see here, I only have these components. Velodyne is not there. It's one of the new features now of the vADAS 3.0 is we are working with NuGet packages. So basically, if you know NuGet, it's you have now a, let's say you have a package of, or you have data source of all the available packages. You just need to click on Browse, and let's search for Velodyne. I'm only searching locally here, and you see I have these vector.da components Velodyne. You click only on this icon, and now it's installing basically. Basically, it's doing nothing but adding these references into your project, so you can use these data. It's still adding them, needs some time, but now it's asking me, do you want to add it? Okay. Now they are added. Okay, now close it. I need to close this also once, and now rebuild the application again, just to make sure that every component knows about these changes. Open the ADL file. And now you see I have the Velodynes right here. Just drag and drop one of them right here. So we have it already. And now I need to define this in my visualization component because I don't have a pin that will pass for this data, for this kind of data, which is point cloud. Just one thing, so close it. I'm going to switch back to my visualization. Okay, click on the GFX configuration. Now you have these data type, which is point cloud. Drag and drop it. We already have a type called point cloud, so you don't need to do anything. And the coordinate is spherical. So basically, you need to scroll right down here, and now we need to attach these the properties. So here the angle, and we need also the polar angle, and we also need the range or the distance of these points. You can change the color of the point cloud. Let's do it, I don't know, green maybe. Okay, so now save. You see now we have this Velodyne also. I'm saving it, close, build the project. Now we will open the main form just to make sure that we add the user interface component that will show now our data. Basically, I've already done one. I added a visualizer basically right here. What you need to do is you select from the toolbox. So you just type visualizer, and this is a vADAS component. Per drag and drop, you can drop it right here. It has a name. I'm going to make it a little bit larger. So let me dock these data. And let me just add one more row for my data because I need them. Here. And just making it bigger. Okay. And basically I need another one. So this is number 3. Let me dock it also. And here we go. Dock. Okay, now we have these 3 containers where the data will be available, will be seen. Let me save this, click on the application host, So this is basically a step where you now assign the the views to these user interface visualization component. I'm putting camera in visualizer 1, the scene view in 2, and Velodyne should be displayed in number 3. Okay, save, close. Let me build it one more time. Start it. Okay, and now this is my data. I'm going to start my simulation and start now my application. And there's at the moment no point cloud. Let me check what the problem. Maybe I just misconfigured the IP address of my point cloud. But this can be done easily, so I'm going to check the data. Oh, it's not connected. Yeah, this is why we don't have. So I need to connect it right here. Save it. Now the data are being transferred to the visualization component. Start. And this is the application. Start now the application. And here we go. So we have now our scene view. We have now our point cloud. We have these data, and we also have they should be now. You see now these yellow boxes, which indicates the radar. Basically, these are the radar detection. This is the car here in front of us. Okay, so I'm going to close this just to switch to one topic or doing two topics. So basically, we have these tasks. We talked about tasks. This means how you can switch between different project tasks if you want. Basically, this one was called play. I'm going to rename it. So I click on this button and say this should be live. For my second task, I need another one. Oh, yeah, and here you will see also which component will be available in this task. In my live task, I want all the components to be available. What I also need is I need a recorder. So I'm going to drag and drop a recorder right here. Basically, very easy. Per drag and drop, you drag the data right here. Everything that you need to be saved. And now we have a new component called recorder. Let's define a new task called recording. So basically, I'm going to click on this plus sign, click on the component settings, and change this to record. Okay, what component should be available? I'm going to say Canopy, Velodyne, and recorder. I don't want the visualization to be available. So basically, this is what I select. Now you start the order. You select the start order. It's okay for now. If I click on save, start, we are rebuilding now the data, rebuilding our project. So here is our application. Okay, now you see we have these two tasks. So basically, I can switch to live and click on start. You see now from these applications set up, you see which components are now active. Basically, we have Canopy, Velodyne, recorder, and the visualization. All of them are now active, and they are displaying data if we switch back to visualization. Let me switch back to recorder. And now if I click on start, it will ask me now where to save the data, or if I already done this setting. So basically, the recorder is saving now to this folder, and now only Canopy and Velodyne. You can see it from the font. It's italic, and this is written just normal, so it's not active. Okay, so basically, we're seeing no data. These are the data from the last buffer. Okay, now we recorded the file. If we go back now here, just let me click right here. Select it. I'm going now to open this folder. And now if I change it to that time, now we recorded this file. So one of these files is now recorded at this time. We can use it now in, let me close it. I'm going to do it very quickly. So basically, we can now drag and drop a player. And this player is basically will replay the data. So let me save it. As you see now, the player also knows nothing about what kind of data it should replay. This is why we need to configure it. So basically, I'm going to close this, save it, and close this view. If you see, I also already added a player. also from the component list. So right-click on this project name and select component, add a player component. It's asking me what type of data I want to replay. So I'm going to select BST because I just recorded BST file. Now we can select where the data is recorded. So here, and this is basically here are my data. If you see now, these are the types of the data I recorded. So I have image, this is the camera, yaw rate, the radar detections, and the point cloud. Just drag and drop it right here. So you say to the recorder, I need all these data to be replayed in my project. So rebuild it to make sure that we know the changes. Open the application ADL file, and the player should now have the output pins with the data, with the type of data. As you can see right here, we can now just connect them. I don't want now to record the data, so I'm going just to connect them to my visualization component. Here we go. Okay, now I'm going to add one more task, and it says, let's say it's replay. So replay. It should only have the visualization and the player. That's all what I need. And whatever this start before, it's okay. So now let me start. Okay. Okay, now, so I'm going to switch to my replay and now click on start. And I think I've chosen the wrong, I'm not sure if I've chosen the correct file. So I might just chosen the wrong file. So let me choose here. Okay, this is my source file, and I'm going to change it to the file that I recorded. It should be, I think it should be this one. They are both done at the same time. So I'm going to switch to this file and try now to replay the data. And as you can see, here are the data that I collected. They are being replied. I can change the speed of replying the data to whatever I want. Okay, now it's done replying. Close. Okay, what we didn't show is how to make the component in between. It's very easy. I will show it in a project where I've done this already because we don't have much time, but it's easy. So basically, this is these component. And in this component, we are just switching the image to gray color, or we are flipping the image. Okay, so you start by right-clicking on the project. You add a component as usual. And now, just 1 second, I'm going to do it with you because we have also a nice wizard that will guide you. So basically, we need a component. If you click on add, these wizards will open up, and it will ask you which input type you have, the name of the input pin and the type of it, and the output pin and the type of it. You describe this, as in my case, I have here an image, and here also an image. You click on add pin, and it will create for you this, basically these components. It's very easy right here. So this is what vADAS created for me, basically not with the code. It just created for me this function. So it says whenever an image comes, you can do whatever you want. So we have as input, we have the image, and as output, as a return value, it's the image. I've done here a small switch case because I defined these settings. So basically, you see this setting at the beginning. It's where you can define a new way to interact with your application. So basically, I have here this setting, and I'm switched between what setting is now selected. So if it's none, I'm doing nothing to this image. If it's a flip image, then I'm going to call these function, and this function is basically the C++ function. This is done very easily. So basically, you use these DLL import, invoking the function from the DLL. The DLL, I already built it. It's a very easy function. I just swap the bytes array of the image data, and basically this is how I'm flipping the image and bringing back. Or in this case, I only have a pointer to my data, and I flip just the order of the byte array. In that second case, I just do the C# code So basically, it runs here. I just gray everything, multiply everything by 99, and create the new image, return it back. In case of nothing, I just return the image back. So basically, this is how it's done. And yeah, this is just one more thing, maybe. Okay, so I'm going to open one more application. I'm sorry. So in the desktop, we also have you have also the option, the ability to also run basically your application via remote client. So basically, I have now my data. You see my application, and this is another application. I'm not going into details, but please just look into the help of vADAS. It describes how you can write your own remote client. Basically, it's an API that you are using. In this case, you see now I have all the tasks defined right here with the same name. So here is live, record, and reply. I can now select live and click on start. Please check this icon. It will now change into start. As you can see now, we have it's already started. So I'm sorry, I need, yeah. So now it's already started. I can also stop the running task. I can also switch to the other task, and now I can also set any of these values of these components. I can set them also per remote client. Just wanted to show you this, and now I just want to say that I came to the end of my presentation. I just hope that you got idea how this is all done in vADAS, and now I'll hand over to Alex.
Okay, thanks, Mohammed. Very nice presentation. So during the last, let's say, 30 minutes, I think we've seen quite a bit from the tool itself and how the different features are then used. So I would now like to ask the audience if there are any questions that you want to voice in the Q&A feature. There have not been questions in the last few minutes, but we can still stick around in the webinar for a few more minutes and try to answer those questions. Okay, so as there are no more questions in the Q&A area, I would like to thank everybody. I want to thank Mohammed for the presentation, and I also thank you in the audience for attending the session. If you should have any more questions in the follow-up, please feel free to address your Vector representative in either subsidiary or here at Vector Informatik in Stuttgart. Thank you very much for attending, and till next time. Bye.